Hey everyone, welcome back to this explainer from the Foundry by Forge College. I'm super excited you're joining us today. So last time in our security implications and synthesis session, we covered the theory behind blockchain security, but today we are getting our hands dirty. We're grabbing our wrenches, rolling up our sleeves, and we're looking directly under the hood of the mining engine to see how proof of work actually runs on a mechanical level. All right, let's look at our blueprint for today. We've got 1, the asymmetric engine, 2, decoding the mining puzzle, 3, the decentralized lottery, 4, verification and accumulated work, and finally, 5, the protocol thermostat. Let's jump right in. Section 1, the asymmetric engine, the core tension of proof of work. You know, the entire secret sauce of proof of work really comes down to one word: asymmetry. On one hand, you have miners sweating relentlessly. I mean, they are burning massive amounts of electricity, using sheer probabilistic brute force just to solve a puzzle. It's incredibly expensive and, frankly, exhausting to find the solution. But on the flip side, checking their work is an absolute breeze. Any standard node can run a single, fast, deterministic check to verify the work. It's kind of like spending 3 whole days baking this wildly complex, multi-tiered pastry, but it only takes half a second to taste it and go, yep, that's cake. That cost asymmetry is absolutely crucial. Moving right along to section 2, decoding the mining puzzle. Let's look at the actual gears of the hashing engine. To really understand this puzzle, you need to meet the nonce. Basically, think of the nonce as a variable dial on a really heavy-duty podlock. The miner acts like a roaring engine that aggressively spins this dial, constantly changing this single-use numeric value in the block header. They're trying millions, actually, scratch that, billions of different number combinations every single second to create new candidate hashes. It is an absolutely absurd amount of raw mechanical effort. But what exactly are they aiming for when they spin that dial? Well, they're trying to produce a hash that falls below a very specific, strict numeric boundary. We call this boundary the hashing target. It's a lot like trying to throw a dart, except you're blindfolded, and the bullseye just keeps shrinking. For a block to be considered valid, that header's hash must be less than or equal to this threshold. If it's not, the network outright rejects it. No participation trophies here. So this setup creates a frantic mechanical loop. Step 1, you build the candidate block body. Step 2, add your header data and spin that nonce. Step 3, compute the cryptographic hash. And step 4, compare that hash to the hashing target. Did it fall below the line? No? Spin the dial again and again. This exact 4-step loop runs billions upon billions of times a second worldwide. It is pure, unadulterated trial and error. All right, section 3, the decentralized lottery. A really relatable mental model for all of this. Now, if cryptographic brute forcing sounds a bit intimidating, don't worry at all. This dynamic perfectly mirrors something we can all relate to. Every single hash attempt a miner makes, it's exactly like buying a single ticket in a massive decentralized lottery. The hashing target, that just determines the number of winning tickets available in the overall pool. And your fixed hardware, that simply determines your steady ticket production rate. So the really crucial takeaway here is this: the probability of finding a winning ticket equals your production rate divided by the total ticket space. You just can't cheat the math. You can't guess the winning number using some clever logic. You literally just have to buy more tickets faster than anyone else. It's a beautifully simple, wonderfully fair brute force game. Which brings us to section 4, verification and accumulated work, checking the engine's output. Eventually, amidst all that wild spinning and hashing, someone hits the jackpot. A miner finds a winning ticket. But before the network actually accepts it, nodes have to perform a rigorous quality control check. And remember that asymmetry we talked about earlier? This is exactly where it shines. The network verifies the header hash beats the target, checks the previous block reference, validates the Merkle root against the transactions, ensures the timestamp is within range, and confirms there are absolutely no double spends. Because this checklist is so fast and deterministic, any node operator, even a student running a node on a dusty old laptop in one of Forge College learning programs, can instantly verify that the massive mining farm actually did the work perfectly. And as these validated blocks start stacking up one on top of the other, we get accumulated work. This is basically the sum of computational effort recorded by successive valid blocks. Each block represents a massive, provable amount of energy and time. Stacking them creates this chain of probabilistic finality that becomes computationally impossible for a bad actor to rewrite. The deeper a transaction is buried, the heavier the accumulated work protecting it. That right there is what makes the whole system virtually unhackable. Of course, in a globally decentralized system, latency happens, right? Sometimes two miners will find a valid block at the exact same time, which naturally creates a fork, or what we call an orphan block. But the network doesn't panic. It resolves this naturally by simply always following the chain with the most accumulated work. The math literally just sorts itself out over time. But this brings up a massive logistical question for our engineering blueprint here. Think about our decentralized lottery for a second. What happens to our lottery if 1 million new miners suddenly plug in their machines and join the network? The ticket production rate would go through the roof. So what prevents winning tickets from being found entirely too fast if the network's hashing power just explodes? And that leads us right into Section 5, the protocol thermostat, adjusting the difficulty. The network actually expects hash rate fluctuations. I mean, the amount of computational power joining or leaving the network changes constantly, depending on things like electricity prices or hardware upgrades. To counter this, the network uses a difficulty adjustment, our built-in thermostat. If blocks are being found too fast, the network automatically shrinks the target, effectively making the subset of winning lottery tickets smaller and harder to find. And if blocks are too slow, it automatically expands the target to speed things up. This difficulty translates the total hashing power into an expected block production rate. It's a thermostat that ensures no matter how much horsepower is thrown at the engine, whether it's 5 laptops in a garage or 10,000 industrial warehouses full of ASICs, the output remains a steady, predictable pulse, keeping intervals to an average of about 10 minutes. It is just such an elegant, self-regulating feedback loop. So, to wrap up our blueprint today, first, cost asymmetry secures the network. It's expensive to find, cheap to verify. Second, the nonce and the target define our mechanical puzzle. Third, mining is essentially a decentralized probabilistic lottery. Fourth, accumulated work securely dictates the true chain. And finally, the difficulty acts as our stabilizing thermostat, keeping the heart beating steadily. But wait, how exactly does the algorithm mathematically calculate this difficulty adjustment under the hood? Well, that provocative question sets us up perfectly for our next explainer. I highly encourage you to visit forge.college to continue exploring this Web3 track. The engineering only gets more fascinating from here. Thanks so much for joining me today. Keep exploring, and I'll see you next time.